Hi everybody. So in this video, we're going to continue with topic 9.2, derivative of a function. So it says a derivative of a function, also known as the derivative function or gradient function, is a function that gives us the gradient of the tangent line at any point. So what does that mean? That means that if you have a graph, any graph, let's say we have this curve, and this curve is f of x. If you are given or you find the derivative of f of x, which we will symbolize with as f prime of x. F prime of x, that's one of the notations that is used to represent derivatives, f prime of x. So the function f prime of x will give us the gradient of f of x at any point. So what does that mean? That means that if you want to know what the gradient of f of x is, say here, the derivative will tell us what the gradient of a tangent line would be at that point, at that specific point. So what if we want to know what the gradient is, say here? Well, we can just draw, again, a tangent line, and the slope will be given by the derivative. So it tells us, basically, whether functions are going up, increasing, or they are flat because you have a maximum, or they are going down because they are decreasing. So here in this table, we have some other notations for the derivative. This one is very common as well, y prime. The problem with this notation is that it does not name the independent variable. It doesn't name x, which is normally the independent variable. Sometimes you will find other independent variables, namely, say, time, for example, is a common one. So you might find an independent variable as t. Anyway, this one, dy by dx, this one is a derivative of y with respect to x. And here it's naming both the independent variable, which is x, and the dependent variable, which is y. And f prime of x, as I mentioned before, is a derivative notation that actually emphasizes on the name of the function and does name the independent variable x. So basically, this is it for the introduction to a derivative of a function. And now we are going to look at some examples on how it is used. Okay, so here we are on example 9.7, and it says, a ball is thrown upwards from the roof of a building. The vertical height of the ball from the ground in meters after t seconds is given by the function h of t, that means height, equals negative 4.9 t squared plus 18t plus 50. The derivative function is given as h prime of t equals negative 9.8 t plus 18. So let's picture the situation. There's a building, and a ball is thrown from the building. Okay, so obviously this would not be like that, but you get the idea of the ball falling to the ground. Now, let's put this on the Cartesian plane. This would be the x-axis, the ground, and the side of the building, the front side of the building, would be the y-axis, right? So this here, this height, is 50 because that is the height of the building. How do I know? Well, because of this number here at the end of the function. At time 0, it's 50. Therefore, that has to be the y-intercept. So the ball is thrown from a height of 50 meters. It goes up, and then because of gravity, it falls back down to the ground. Here they give us the derivative, but I want to show you guys how to find a derivative because it's pretty simple. It's not part of your course, but when you go to college and if you have to do calculus, you will need to know how to do them. So I'm going to teach you how to do that very quickly. Okay, so if h of t is equal to negative 4.9 t squared plus 18t plus 50, what is the derivative? So the rule for differentiation of these type of equations that are polynomial is very simple. What you have to do is grab the exponent of the variables and multiply it by the coefficient. And also you will have to subtract 1 from the exponent. So here we would get 2 times negative 4.9 t to the power of 2 minus 1. For 18t we do the same thing, so that would be 1 times 18 and t to the power of 1 minus 1. For 50, because it's a constant, you could say that it is multiplied by x to the power of 0. So if you multiply by 0, this eliminates. Okay, so any constant will not appear in the derivative. And this would give us negative 9.8 times t to the power of 1, right? Because 2 minus 1 is 1, plus 18, because t to the power of 1 minus 1 is t to the 0, and t to the 0 is just 1, right? So we don't even write it. So notice that this is the same as what they are giving us. Okay, so we're going to use the derivative to solve the problem they're giving us. So it says letter A, find the initial velocity. So let's get rid of this. The initial velocity is what was the velocity when the ball was thrown. Now the initial velocity is not 50, obviously, right? That's just the height. The initial velocity is given by the slope of this line, because that means that this is the velocity, right? If this is distance, or height, I should say, if this is height and this is time, a slope would be height divided by time, and that's distance divided by time, therefore velocity, right? So the initial velocity of the ball, that occurs at time equals 0. So at time equals 0, the velocity, which is the derivative of the height, would be then negative 9.8 times 0 plus 18. And this equals 18. So the initial velocity had to be 18 meters, because we're talking about height in meters, and time is in seconds, so meters per second. Then we have part B. For part B, it says, find the time at which the velocity of the ball is 0. Interpret the meaning of this. So that means when was the velocity equal to 0? So that means when was negative 9.8 t plus 18 equal to 0? So we solve for t, right? So we would get that t is equal to negative 18 divided by negative 9.8, and this is about 1.84. So 1.84 seconds. At 1.84 seconds, the velocity of the ball was 0. What does that mean? So if you look at the graph, because the derivative gives you slopes, the slope was 0 here at a maximum, right? That's where you have a slope that equals 0. So that means that the ball reached a maximum height after 1.84 seconds. So if you look at the x-axis, this here has to be 1.84. So for part C, we need to find when it hits the ground. That's right here. At what time does it hit the ground? In other words, at what time was the height equal to 0? So we have to solve minus 4.9 t squared plus 18t plus 50 equals 0. So you can plug this into the calculator, into the app for functions, solving polynomial functions, the polynomial solver, and you will get that t equals either 5.52 or t equals minus 1.85. But because this answer is negative, it doesn't really matter, since we are describing a real life situation. So it has to be after 5.52 seconds. So that means that after 5.52 seconds, it reaches the ground. But that's not the question. The question is, what was the velocity? So we have to plug this into the velocity function. So what is this plugged into the velocity function? At 5.52 seconds, what was the velocity when the ball hit the ground? So this will be this, just negative 9.8 times 5.52 plus 18, and this is going to give us negative 36.1. Negative 36.1, and because it's velocity, we have to say meters per second. Now this makes sense because the ball is going down, right? So the slope of the line at that point of impact tells us how fast the ball was going, and it's a negative speed because of the direction of the speed, which is going down. Okay, guys, so after that example that we just saw, you're going to find exercise 9.2. Please do the problems in the section, and if you have any questions, I will be happy to help you out. Very well, so we continue now with 9.3, which is a section that talks about interpretations of the derivative. So on this graph to the left, we have something that says positive gradient. So notice that these are all straight lines that are going up, and if you look at them from left to right, they're going up in the upwards direction. So that's why this is what's called a positive gradient. A zero gradient occurs when you have horizontal lines, right? So if you have a horizontal tangent to a graph, it means that the gradient at that point is zero. And likewise, if they are going down, right, always looking at them from left to right, if they are going down, then you have a negative gradient. This is useful for the interpretation of the derivative, because if you get a derivative that is positive, it means the gradient is positive. Therefore, the function is increasing at x, at that value x. If it's equal to zero, the gradient is zero, so the function is constant. It's neither increasing nor decreasing at x. So that's something like this. If you have a curve that looks like this, and the gradient is zero here, it means that this is a maximum. Or likewise, if it's here, it would be a minimum of the graph, where the gradient is zero, because the function is constant at that point. It's not going up or going down. If the derivative is negative, then you have a gradient that is negative. Therefore, the function is decreasing. For example, here, if you have a gradient that is negative at this point, it tells you that this function is decreasing at that point. All right, so now we are on example 9.8, and it says, given the derivative f prime of x equals x squared minus x minus 12, identify intervals where the function f is increasing or decreasing. So this is the derivative of f. And the derivative of f is going to describe the graph of f. Okay? So it's going to tell us what's going on with the intervals where f is increasing or decreasing. So what we have to do is equal the derivative, first of all, to 0. So if you equal this to 0, 0 is going to be the points where the graph of f is increasing or decreasing. Let's suppose that f looks a little bit like this, goes back down and up. The solutions to this would be this point here and this point there, right? Because that's where the slope of the curve equals 0. So it would tell us where you have a maximum and a minimum. So this would be a maximum and this would be a minimum. The advantage of this is that also we can find out where the graph is increasing, where it is decreasing, and where it is increasing again, for instance. Supposing the graph looks like this. So I'm going to show you how to do it algebraically, and then I'm going to show you how to do it using the graphing calculator. So this is f of x, right? So the derivative is going to describe the situations for f of x. So the derivative is x squared minus x minus 12. How do we solve this for x? Well, you can factor, because this is the same as saying x minus 4 times x plus 3. How do I know that? Well, negative 4 times 3 equals negative 12, and negative 4 plus 3 equals negative 1. So that tells me that this has to be the factorization of that function. If you can't do it this way, remember you can use your calculator, right, to find these values for x. So we're going to get that x equals 4 and that x equals negative 3. So that means that at these points we have either maximum or minimum for the graph of f of x. So what you do is that you grab these values, negative 3 and 4, and you draw a table. Okay? So here we know that for these points the slope is 0. So this is 0 and this is 0. So I need to find out what happens to the graph before negative 3. So value before negative 3 would be negative 4. So what happens to the graph before negative 3? So let's plug in negative 4 into the derivative. So if I plug that into the derivative, if I plug in negative 4 there, I'm going to get, and you guys can do it yourselves, 8. Now because 8 is positive, it means that the graph is increasing. It has a positive slope. So the graph is going up and going up and going up until it reaches probably a maximum. So theoretically here the graph should be going down. We're going to verify that. So let's plug in a value between negative 3 and 4. The easiest one is always going to be 0. Okay, so if we do 0, we plug it into the derivative, it's going to give us negative 12. So because this is less than 0, effectively it's going down. It has a negative slope at that point. So it's going down. Then here it reaches 0. After 4, let's see what happens. So let's plug in 5 into the derivative. So if you plug in 5 into the derivative, you're going to see that you also get 8 again. And 8 is greater than 0, therefore the graph is going up. It's increasing. And notice that this is more or less the situation that we have here with the example I used, f of x. So this would be a maximum, where x equals -3, and it would be a minimum where x equals 4, as you can see. Because before -3, the graph is going up. You can see that here. It reaches a maximum where the slope is 0. Then it starts going down because at points after -3, the slope is negative. Then you reach a minimum at x equals 4, and then it goes back up. But what they are asking us is to identify the intervals. So what are the intervals? Well, when x is less than -3, when x is less than -3, the function would be increasing, right? When x is greater than -3, but less than 4, the function is decreasing. And finally, when x is greater than 4, so when x is greater than 4, the function is increasing. And those would be the intervals, right? Notice that we don't say equal to, because at those specific points, it's not increasing or decreasing. Those are stationary points where the slope is 0. All right, so here we are going to do the same thing, but now graphically. Notice that I've already gone to y equals to plug in the equation. In this case, the derivative, right? X squared minus x minus 12. So if I hit the graph button, I get this. So what this function is going to tell us is what are the intervals where the function or the gradient of the function is positive. So very importantly, we need to know what are these intercepts, because this is where the function is going to be 0, right? Remember that we found that these points were -3 and 4. So notice that before 3, it's positive, right? The function or the derivative of the function is positive. So that means that you have positive gradients. Then between -3 and -4, the function is negative, right? Because this part of the graph is negative. In terms of y, right? We're always talking about y, but this is the derivative of f of x. So here, the derivative is negative. Therefore, it means that f of x is actually decreasing. And finally, after 4, this is increasing. That tells us that the gradient of f of x is positive. Okay, so next you're going to find example 9.9, and it says the rate of change of a population is given by the function. Notice that this is a rate of change, dp over dt. That means change in the population with respect to time is equal to 4 over t plus 1, where p is the population in thousands, and t is the time in years, and t is greater than or equal to 0. Letter A, find the initial rate of change of the population. So the initial rate of change is when time equals 0. So if we plug 0 here, what's going to be the initial rate of change of the population? It's going to equal 4 over 0 plus 1, and this is just going to be 4. So it means that the initial rate of change of the population was 4,000 people, right? People. And this is per year. So that was the initial rate. The population was increasing at a rate of 4,000 people per year. For part B, they ask us to describe how the population changes over time. So the easiest way to do this is by graphing. So next I'm going to show you a graph of this function. So here is the graph. Notice that I plugged it in as 4 divided by x plus 1. Be sure to use parentheses in order to get the right graph. So when you hit graph, this is what you see. Now this is the rate of change of the population. So you can see that the initial rate of change, like we found, was 4, because this is 4, obviously, so 4,000 people. Then you can see that the rate of change is just decreasing, 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 decreasing. So that means that in the case of this population, the rate of change, the rate of increasing of the population is approaching 0. Okay, so here we are now on example 9.10, and it says, given the derivative, dy dx shown, so this is dy dx. Write down the intervals where y is increasing and intervals where y is decreasing. So this is not y, but rather the derivative of y. So the derivative of y is going to tell us where y, the original function, is increasing or decreasing. And that's very simple to find. It only depends on the sign of the graph, right? Before and after or between these points. So here we have a negative graph. Here we have a positive graph. Here we have a negative graph. Here we have a positive graph. Let's see where else. We have a negative graph here and a positive graph there. So that will tell us the intervals, right? So let's just put them in order. So when x is less than a, we have a graph that is decreasing. How do I know? Well, the derivative is negative, right? Notice that before a, we have negative derivatives. So if x is greater than a, but less than b, then the graph is increasing. Why? Because it's positive here between a and b. And we can say that if x is greater than b, but less than c, it's going to be decreasing. Then if it's between c and d, so we would say, but if it's greater than c, if x is greater than c, but less than d, it is increasing. If x is greater than d, but less than e, decreasing again. And then finally, if x is greater than e, it will be increasing. Very well, so that would be it for this video. After that example that we just did, you're going to find exercise 9.3. So as usual, please do those problems. And if you have any questions, I will be very happy to answer them for you. Please take care and God bless.